All right, so in this small video, what I want to do is just illustrate visually convergence of a power series. So for example, I wrote this small little MATLAB code that's just going to visualize a function for us and then visualize its power series term by term. So here's our first power series that we're going to consider. It's just our friend 1 over 1 minus x. And we're plotting this between x equals -1 and x equals 1. So again, this black line is just the function 1 over 1 minus x. So let's see what happens if we just have one term of our power series. So the line that just popped up in red is when we only include the first term of its power series representation. It's just a horizontal line with a value of 1. Well, let's see what happens if we add two terms. So this is, again, including the n equals 0 term and the n equals 1 term of our power series, but no other ones. So the n equals 1 term, the highest power of n, is 1. So it's an x to the first. We see a line pop up. And this line has a non-zero slope. And we can see it looks like it's touching this function pretty well around x equals 0. Let's include more terms. So if we include 3 terms in our power series, the n equals 0, n equals 1, n equals 2 term, so we're up to the x squared term now, we see that, well, we're starting to basically hug the function 1 over 1 minus x by our approximation in red. And we can keep including more and more terms. And the more terms of our power series we include, the better our approximation gets to that actual function. So here's a very useful idea for power series, is if we have this function, here we have 1 over 1 minus x. Well, you know what? If we rather just work with a power series approximation, maybe we just include the first 6, or maybe the first 10 terms or 11 terms of its power series. Because you know what? The first 11 terms, it looks pretty good for most of these x values here. We're starting to see some error kind of around x equals 0.8 and higher, or maybe smaller than x equals minus 0.8. But otherwise, just visually eyeballing it, this approximation looks pretty good. And you might be wondering, why would we want to do that? Well, if we have a power series, remember, it's basically an infinitely long polynomial, except we're only saying, you know what? Include the first 11 terms of that polynomial. Well, polynomials are functions then that we can easily integrate and easily differentiate. So manipulating power series approximations to functions is even easier. So again, we can keep including more and more terms and just visually adding the first maybe 40 terms of this power series, 39 terms. This power series approximation does pretty well in approximating the true value of this function. Well, let's check out another power series. This next power series example we'll do is for the function 1 over 1 plus x squared. Now, you might remember in a couple videos ago where we figured out what this power series of this function was using the idea of stencils and power series representations of functions, or representations of functions using power series. The thing that we noticed as well was every single term in the power series only has even powers of x. So we only have x squareds, x to the 4th, x to the 6th, x to the 8th, and so on. Well, let's see how good successive approximations to this function are. So what happens if we just include one term of its power series? Well, we have another horizontal line with a value of 1. Groovy. Let's add the first 2 terms of this power series. So the first 2 terms now, again, because we only have x squared type terms, or even power of x's in this power series of the function 1 over 1 plus x squared, this looks like a parabola face down. Okay, well, let's add the first 3 terms. It looks like we're hugging that function or approximating that function better and better. And again, the more terms that we add into this power series, the better approximation of this power series is to the true function. And by the time we start getting into double digits, we're approximating this function pretty well. The first 30-ish terms or 29 terms, we approximate the function 1 over 1 plus x squared rather well using this 29-term polynomial. Again, polynomials are nice because we can integrate, we can differentiate them just through power rule. Whereas if we had a much more complicated function, here 1 over 1 plus x squared, if we wanted to integrate that, we get to do trig sub. Whereas if we want to just integrate a power series approximation, we only have to do antiderivative power rule. So the big thing to note from here is the more terms we have in a power series, the better approximation a power series is to the true function. Although sometimes in science, mathematics, or engineering, you might only use the first couple terms of a power series because that might only be good enough for whatever approximation or for whatever study you're doing.